Hi guys, so this is our second video. It's about kinematic equations. Now the kinematic equations we discussed in the class already. So the first week we discussed along with the units. So I am going to write down the kinematic equations directly. But before that, let me actually do a quick review on the definitions of each term. So we discussed velocity. I'm drawing this arrow. You know why I'm drawing that arrow, because velocity is a vector. And the velocity is the change in displacement divided by change in time. We know that, right? And then the acceleration, again, a vector. And that would be change in velocity divided by change in time. So these are the key factors. Delta x stands for the displacement. Delta t is the time change. Delta v is the velocity change. And delta t again is the elapsed time or the change in time. So most of the time people actually use it as delta x divided by time directly instead of using delta t. And then the same over here, delta v over time, just like that. Okay. Now let me actually write down the kinematic equations, the equations that we already know about. So let's write the first equation. There's no actual order for this one. So I write V final equals V initial plus AT. So this equation, if you look at it carefully, it does not have the term displacement. Do you see any delta x in this equation? You don't, right? Yeah, so this equation does not have delta x term in it. And then the second equation we learned in the class, delta x, the change in displacement, equals to V initial times time plus 1/2 multiplication A here, half times A, and then t square. Many students forget to square the t, but please remember this is a t square. And then the last equation is V final square, V initial square plus 2 times A delta x. So these equations are used or can be used in either direction. When I say either direction, that means it can be used along the horizontal direction or along the vertical direction. So we only know about the horizontal direction at this point. We don't know a whole lot about the vertical directions, right? So in the horizontal direction, I just introduced the number line to you guys. And here you have the positive direction, that is positive, and in the opposite direction, you have the negative, right? This is actually a convention. There is no set rule to say that the right word is positive and the left word is negative. But this is just the tradition, and we go along with that. As I mentioned in the class, if someone wants to say the left word is the positive and the right word is the negative, that's completely acceptable, but you have to say that's what you did when you are doing a problem or in the quizzes and exams. So when I was using, or when we are using these things, these equations, first thing that you have to do is, especially when you are doing a problem, you have to find out the given information. Identifying what is given is very important. So in order to get to that, let me actually share the screen and do a sample problem, okay? So let's see if I can share the screen with you. Okay, so this is actually the same document that I shared. These are some of the problems that we have on the on the blackboard, and they are copied from the OpenStax textbook that we are using. So I like to do problem number 1. So at this point, you guys can go ahead and, pause the video and read it. But I'm going to write down the given information. So let's read the problem first. An Olympic class sprinter starts a race with an acceleration of 4.5 meters per second square. So in this problem, it clearly gives you the word acceleration and the corresponding units. So we have to watch out for 2 things. One is what we are looking at, and the second is if it is given in the correct SI units. So in this case, we have acceleration and given it as 4.5 meter per second square. And the question asks, what is her speed 2.4 seconds later? Now, the problem states that the sprinter starts the race with an acceleration 4.5. So when someone is starting a race, that person's initial velocity is 0, right? So at this point, we have two things already: the initial velocity to be 0, acceleration to be 4.5. So I am actually going to stop sharing this and write down what we have. So 4.5, let me quickly draw the table, and I'm going to get back to this one because otherwise I will forget these numbers when I stop sharing the video. So on the table, I mark VI, VF, A, T, and delta T. So the sprinter starts, and when someone is starting a race, obviously that person has a 0 initial velocity. And then the acceleration the person has is 4.5 meter per second square. And the question, part A, asks, what is her speed 2.4 seconds later? So that means the problem gives us the time also, and the time is 2.4 seconds. Now I'm going to stop the video. I'm not the video, but the screen share. And this is what it looks like. So initial velocity is 0. Final velocity we don't know. And time acceleration is 4.5. Time is 2.4. And then we have delta x. Actually, this should be delta x. So having a table like this is very helpful because after getting this table done, you really do not have to go back and check the problem. So what we are to find is the final speed, because the question asks us to find her speed 2.4 seconds later. So we have V initial, we have the acceleration, we have the time, and what is missing is V final. So in order to address this problem, we have to go back to these three equations and decide what equation fits best. Now, this is another place where you can pause the video and think before I give the answer. And hope you did and decided what equation you need to use. And I am going to use the first equation where you have V final. That's what we want. V initial plus A times T. Since this is happening along a straight line, I didn't really put the vector sign because the arrow actually represents the direction. So clearly this is pointed along the x direction. So you don't have to worry too much about the direction. Actually, when we get into the projectile motion or 2D motion, that really matters, but let's not talk about it yet. And then VF equals V initial plus A is 4.5. Where is it coming from? From the table. And if you like to just, use the units, that's fine too. And then here you have 2.4 and seconds. Don't misunderstand that as a 5. It is 2.4 seconds. And then 1 second and 1 second cancels out. So let me quickly get the calculation, which is 4.5 times 2.4. And I get 10.8 meter per second. So please check if the answers are correct on your own. So there you have 10.8 meter per second. And this is the final velocity of the sprinter, or the velocity of the sprinter in 2.4 seconds. And there is a second part to the question. Let me actually go back and check again. And the second part is sketch a graph of her position versus time for this period. So the second part is sketching a graph. Now, in order to sketch this graph of her position versus time for this period, meaning for the 2.4 second time, we need to find her final position. That means we have to find the delta x. So let me actually get I believe you can see this, yes. And then before you do that, now finding delta x That's our next task before we start plotting the x versus time graph. So in order to do that, we can choose another equation, meaning to find delta x. So this is again a time to pause the video and decide on your own. So here's what I have. These are the three equations. So delta x is what we want to find. So there are two equations with delta x involved. You can pick either of the two. There's no big issue with that. So I am going to choose delta x equals VIT plus 1/2 AT square equation. That's my second equation. Okay. So let's write it down. Delta x equals VIT plus 1/2 AT square. And delta x VI, that's 0. V initially is 0 according to the table over here. And then plus 1/2. A is 4.5 and T is 2.4. Don't forget to square that. So in this case, I did not really include the units. Since everything is in SI units, I know that I am going to end up with a unit in meters for this one. So I'm going to pause the video and get my calculator and get the number again, get the value again. So I got 12.96 as the answer. So it is 12.96 in meters. So we are supposed to plot position versus time graph, guys. So here you have the position, delta x, and there you have the time axis, right? So let's talk about the points that you know. So at t equals to 0, the position also was 0 because the sprinter has not displaced yet. And then after 2.4 on the axis, here you have 2.4 seconds, and the person has moved 12.96. So on the x-axis, let's mark 12.96 in meters. So where do you put that? You put it right over here. Okay, and then this is the second point. Now what happens in between? Now you recall the slope graphs that we did in the class. So delta x over versus time graph. The slope always gives us the velocity. So if I draw a straight line from here to here, that indicates our velocity is constant. But as you guys saw, the velocity is not a constant. Initially, we have a velocity of 0, and then we have a 10.8 meter per second. So clearly, the velocity is increasing, right? So the straight line idea is not going to work. And as we discussed, we have to have something that actually goes up. Like, so the slope is increasing as you go up. Maybe this is not the best drawing, but you guys can understand what I am saying. Initially, there shouldn't be a slope because we start from 0, and then as you go, the velocity is increasing. So this is the type of graph that I am expecting. I hope this made lot of sense. If not, please ask. We can talk about this in the class. Again, I don't want to make the video too long. All right. See you with the third video tutorial next week.